Hello everyone. Let's start today's journey with a question. Have you ever thought about why carbon is called the element of life? Whether it's the food you eat, the clothes you wear, the medicines you take, or the fuel that powers your car, carbon is at the heart of it all. Now, here's the fascinating part. The secret to carbon's versatility lies in the way it bonds. Unlike metals, which often form ionic bonds, carbon prefers something different, the covalent bond. Carbon has an atomic number of 6. That means its electrons are arranged 2 in the first shell and 4 in the second shell. These 4 outer electrons, or valence electrons, make carbon tetravalent. But here's the challenge, carbon can't easily gain 4 electrons, that would mean having 10 electrons held by just 6 protons, which is unstable. Nor can it easily lose 4 electrons, that would require a huge amount of energy. So, carbon takes a clever middle path, it shares electrons with other atoms, achieving stability without the extremes of full electron loss or gain. And that's where the magic of covalent bonding begins. A covalent bond forms when two atoms share one or more pairs of valence electrons. Think of it like two neighbors sharing a fence, both benefit from the arrangement. When two hydrogen atoms, each with one electron, come together, they share a pair of electrons. This creates a single covalent bond, which we can write as H-H. In electron dot diagrams, we represent shared electrons as pairs of dots or crosses. Oxygen is different. Each oxygen atom has 6 electrons in its outer shell, needing 2 more to complete the octet. So, two oxygen atoms share 2 pairs of electrons, forming a double covalent bond, written as O double dash O. Nitrogen is even more striking. Each nitrogen atom has 5 valence electrons and needs 3 more. By sharing 3 pairs of electrons, nitrogen atoms form a triple covalent bond, written as N triple dash N. You'll notice the pattern. The number of shared electron pairs tells us whether the bond is single, double, or triple. And as we'll see later, this number also affects bond strength and properties. Let's now look at a classic example, methane, chemical formula CH4. Carbon has 4 valence electrons and each hydrogen atom has 1. By sharing 1 electron with each of 4 hydrogen atoms, carbon forms 4 single covalent bonds. In the electron dot diagram, carbon is at the center, each bond represented by a shared pair between C and H. Methane is a major component of biogas and compressed natural gas, CNG, making it both a clean fuel and an everyday example of covalent bonding. Here's an important point. Covalent bonds within the molecule are strong, but the forces between different methane molecules are weak. That's why methane has a very low boiling point and is a gas at room temperature. And because there are no free ions, methane, like most covalent compounds, does not conduct electricity. So, what do covalent compounds generally have in common? First, low melting and boiling points. The intermolecular forces are weak, so it doesn't take much heat energy to separate molecules. Second, poor electrical conductivity. Since covalent bonding doesn't create charged particles like ions, these substances can't carry an electric current. Third, solubility patterns. Many covalent compounds dissolve in organic solvents like ethanol or benzene but are insoluble in water. These properties all stem from the same cause, electrons are shared, not transferred, so there are no strong electrostatic forces holding a giant lattice together as in ionic compounds. Here's where carbon truly shows its versatility, its allotropes. In diamond, each carbon atom bonds to 4 others in a rigid, 3-dimensional structure. This makes diamond the hardest natural substance and an excellent insulator. In graphite, each carbon bonds to 3 others in flat hexagonal layers. One electron per atom is free to move, making graphite an excellent conductor of electricity. These layers slide over each other, giving graphite its slippery feel, perfect for use as a lubricant or in pencils. And then there's fullerene, like C60, where carbon atoms form a hollow sphere resembling a football. This arrangement has exciting potential uses in nanotechnology and materials science. All these forms are pure carbon, their differences come purely from how the atoms are bonded. Let's put this into practice with a solved example. Example 1, carbon dioxide, CO. Step 1, carbon has 4 valence electrons, oxygen has 6. Step 2, carbon shares 2 electrons with each oxygen atom and each oxygen shares 2 back. That gives us 2 double covalent bonds, one on each side of carbon. Step 3, in the electron dot diagram, carbon sits in the middle with 2 double bonds, each shown as 2 pairs of shared electrons to the oxygens. Example 2, ammonia, NH. Step 1, nitrogen has 5 valence electrons, each hydrogen has 1. Step 2, nitrogen shares 1 electron with each hydrogen, forming 3 single bonds, leaving 1 lone pair of electrons on nitrogen. Step 3, the electron dot diagram shows nitrogen at the center with 3 shared pairs, 2 hydrogens, plus 1 lone pair. These rules, completing the octet and sharing electrons, guide the drawing of any covalent structure. So, let's wrap this up. Carbon doesn't usually gain or lose electrons, instead, it shares them, forming covalent bonds that can be single, double, or triple. These bonds create molecules with strong internal bonds but weak forces between molecules, explaining their low melting and boiling points and poor conductivity. The different bonding arrangements in carbon give us diamond, graphite, and fullerenes, proof that the same element can behave in remarkably different ways. From the methane in your gas stove to the diamond in jewelry and the graphite in a pencil, covalent bonding in carbon is all around you. I hope you now have a clear understanding of how covalent bonds work and why they make carbon such a remarkable element. See you in our next session where we'll uncover more fascinating chemistry that shapes the world we live in.